Hi, I'm Chem's best friend, and today we will dive more into Lewis dot structures and learn more advanced structures. So if you're interested in private tutoring lessons, the information is on the screen below. Are you ready? Let's jump in. In a previous video, we had a really nice introduction to Lewis dot structures. We also learned about valence electrons and how many electrons each element has. We could see that they follow nicely column numbers, and we went over the rules. And today we're going to jump a little more in. Let's go. Here is our next structure. We have SF4 sulfur tetrafluoride. We ready? So we're going to stick sulfur in the middle and each fluorine on the outside. Why? Also remember, nature loves symmetry, and stick more electronegative element on the outside. Let's count our valence electrons. Sulfur comes with 6, and we have 4 fluorines, each comes with 7. So together gives us 34 valence electrons to work with. We're going to stick 2 electrons for each bond. Here we go. And then we're going to do our octets from outside in. Remember, that was the rule that students break and things fall apart. And you are not going to do that because you will follow rule number 4. So we're going to do our octets from outside in. Let's give each fluorine 8 electrons around it. All right. Here we go. I am done. I'm going to count quickly and say, okay, sulfur has an octet, things are good. Each fluorine has an octet. However, I only used up 32 electrons. There is 2 left over. So what do we do? Remember, if there is any leftover electrons, it says we're going to place them on a central atom. Okay. So let's put our 2 more electrons on a central atom. Here is on sulfur, and I'm going to actually put them in a little circle to make sure that they are visible. And now we're going to double check everything. And you see a problem? Let's count the electrons around sulfur, and we can see it's 10. It's not 8. So we have 10. And is this okay? And the answer is yes. Sulfur can have more than 8 electrons around it. And why? Well, remember, look, sulfur is in this third energy layer. And third energy layer, if you remember from your electron configurations, also has d electrons, d orbitals. It has d orbitals. So, for that reason, we think that d orbitals are somehow involved in bonding. And sulfur and these elements, now keep going below, can have more than 8 around them because they are in the third energy layer and more, and they have d orbitals around. So this is okay. Now, never, ever, ever put more than 8 for these elements. They're in a second energy level. There is no d orbitals. They cannot have more than 8. Okay? So is this okay? Maybe we should write this. Yes. So third energy layer and more can have more than 8 electrons around, because we think the orbitals are involved. Okay, let's get to the next one. We have our ammonium ion, right? So we're going to stick nitrogen in the middle, hydrogen's on the outside, and we're going to do our count. So nitrogen comes with 5 valence electrons plus we have 4 hydrogen, each comes with 1. But this is why I chose this. We have this positive charge here. Positive charge here means we have to remove that 1 electron. So we're going to do -1 for a total of 8 valence electrons. for a total of 8. So we're going to put 2 for each bond. Yes, 2 electrons for each bond. And then we're going to do our octets from outside in, but hydrogens are done because they can only hold 2. Now we're going to check. Nitrogen has 8. We are good. And you say, okay, we're done. Not quite. Because it's a polyatomic ion and it has a charge on the outside, we need to put polyatomic ions in the brackets. And then we're going to put the overall charge outside in the upper right corner. So now we're done. Okay, let's go here. BH3. So what are we doing? We're sticking boron in the middle, hydrogens on the outside. We count our valence electrons, and boron comes with 3, plus 3 times hydrogens, each comes with 1. I have 6 valence electrons to work with, and I'm going to do 2 for each bond, right here, 2 for each bond. Okay, I'm done. I used up all 6. I double check. Hydrogens have their octets filled. Remember, for hydrogen means 2. That's great. And I look for boron, but boron has 6. Doesn't have an 8. Doesn't have an octet filled. So the rule says if a central atom doesn't have an octet and you run out of the electrons that you have to play with, you have to think of double or triple bonds. But I cannot do it. I cannot bring anything. I cannot shift. So is this okay? Can boron have less than 8? Can boron have less than octet? And the answer is yes. And so here is the exceptions to the rule. I'm going to write that boron and beryllium can have less than 8. Less than 8 electrons around them. Now why? Well, we already saw the exceptions where you can have more than 8. Boron and beryllium are the only 2 that can have less than 8 because they are very, very small atoms. They will be the smallest atoms that will be central atoms involved in covalent bonding. Because they are your 2 smallest atoms that will ever be in the middle, they can have less than 8. Okay, keep them in mind. Okay, let's go here. Ooh, nitrate, our polyatomic ion. All right, let's stick nitrogen in the middle. And let's stick oxygens on the outside. Oxygens are also more electronegative, and remember, nature loves symmetry. So nitrogen comes with 5 valence electrons, and we have 3 oxygens, each comes with 6. But have a look here. Look, we have an overall charge of -1. That means we have to add that 1 electron. So when we do that, we have 24 valence electrons to work with. Okay, let's do it. We're going to do 2 for each bond, and then we're going to do our octets from outside in. So let's fill our octets. All right, here we go. I used each oxygen has 8, and I have 3 of them. I used 24, and I check. However, my nitrogen does not have an octet. It only has 6. So I have to think about possibility of a double bond. Let's think about this. What am I going to do? Well, I can take these electrons from this oxygen and I can move them here. I can also take, let's change some colors here. Can also take these electrons from this oxygen and move them here. And I can also do an orange possibility, take these electrons from nitrogen and put them here. So what am I going to do? Which is the best choice? Well, the thing is that every one of these choices is just as good. And should remember our brackets. So when I have 3 equal choices, this is called resonance. And I actually have to draw it all out. Yikes! Yes, we have to draw it all 3 times. Oh my goodness. Let's go. Let's do it fast. Remember, this was our choice number 1, was to have double bond here. Boom, 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 boom. Quickly move this, and our octets right here from outside in, and our brackets. So this was choice number 1. our choice number 2 was right here, and to do double bond on this oxygen right here. And these guys have their octets right here. That was choice number 2. And choice number 3 was right here, and to use the oxygen on the bottom. Okay, so the thing is that every one of these choices is the same, is equal, and we're going to put it with a double arrow like this, with a single arrow with 2 ends. And do we have experimental evidence? What's going on here? So the thing is that the truth is the real structure is somewhere between them. Okay, somewhere between them. If single bonds are longer than double bonds, and double bonds are longer than triple bonds. So if we take nitrate and we actually measure distance between the nuclei of oxygen and nitrogen, and if any one of these structures was correct, and we give this to the special machine that can measure distances between nuclei, if one of these structures was correct, we would get an answer saying there is 2 bonds which are longer, meaning there are 2 bonds which are single bonds, and 1 bond that is shorter. However, this is not what the machine tells us. So when we actually measure distances, the machine tells us that there is all bonds are same length, and the distance between the 2 nuclei actually is somewhere between a single and a double bond. So that means that these electrons, which are like right here, jump really fast then here, and then they jump really fast here, and then they keep going, and they move here, and then they move here, and then they move here. And they move really, really fast. So it's the truth is it's somewhere smear. So this is why this is a little bit advanced Lewis dot structures. Remember resonance, when you have equal choice of where to form a double bond from. If you have like 2 oxygens or here 3 oxygens, you have to draw all of the structures because the real structure is somewhere in between. So here was resonance. One more. Are you ready for one more? All right. SCN minus. So let's draw it out. So we're going to draw many times the way it is. Now also remember, carbon is the least electronegative. So we will stick carbon in the middle because nitrogen and sulfur are more electronegative. So we're going to put S, C, N. Let's count our valence electrons. Sulfur comes with 6. Carbon comes with 4. Nitrogen comes with 5. And we have to add that 1 more. Yes. So we have 16 valence electrons to work with. Here we go. And we're going to put 2 for each bond. And we're going now work our octets from outside. Outside first. Outside in. All right. So I'm going to actually quickly draw this bracket here. Okay. So let's quickly check. We have each sulfur has 8. That's great. Nitrogen has 8. That's great. I used up all 16 valence electrons that I had to work with. But carbon has 4. So I have to think of a possibility of a double bond. And you say, aha, resonance. But before, when I had nitrate, I had 3 equal choices. I had 3 oxygens to choose from. But here I do not have equal choices. So can I do choice number 1? Meaning take the electrons from sulfur and put them here and make 1 triple bond. I can do choice number 2. Let's make choice number 2 green. I can take electrons from nitrogen and make a triple bond here. Or can do 1 more choice. Let's make it maybe purple. I can take then these electrons here and then these electrons here and make 2 double bonds. So here is my different choices. And which one is the best? Well, we don't know right now. And we have to quickly, well, let's draw them out and then I'll show you what we're going to do. So choice number 1, remember, was S, C, N. And this was then a triple bond, we said. And this one was here. And then we will leave these electrons here. Here is 16 electrons. Here is our negative, okay? Choice number 2 was green. So we have S, C, N. We're going to do our triple bond here, right? Yes, and we will do our single bond here. We do our bracket. Here is our 16 electrons. And the third choice was to do a double bond from each end. And we're going to have these electrons here. Here we go. And remember our brackets. Okay, which one is the best? To help us decide, we have to introduce a new concept. We're going to do formal charge. Okay, so what's formal charge? Maybe I should write a formula. So formal charge is a way of keeping track of electrons, and we're going to assume that electrons are shared perfectly, and half of the electrons will be assigned to one atom and half to the other. And so basically it's this. It's number of valence electrons an atom came with minus, you ready? We'll put a bracket, minus number of lone pair electrons plus, here will be half of bonded electrons. So this is what formal charge equals, number of valence electrons. But you say, this is hard. Okay, so I'm going to show you how we're going to do this. We're going to take maybe yellow and we will separate things. So see these 6 right here, 6 valence electrons? I'm going to draw a line between them. We'll split this up and these ones will split up. So let's do our formal charge. Sulfur came with 6, right? And now it has, well, how many lone pair electrons? 2. And here is 6 bonded electrons, but we will count only half of them. That's why I separated them, yes, in the yellow line. So sulfur came with 6, and now it has 5 around. So 6 minus 5 is positive 1. Carbon came with 4, and it has no lone pair electrons, but it has here 6 bonded and here's 2. So it has 8 bonded electrons. So half of bonded electrons is 4. So carbon came with 4 and now it has 4. So formal charge is 0. Yes, okay. So nitrogen came with 5. And now let's quickly count. Well, nitrogen came with 5. Well, how many lone pair electrons? Here are my lone pair electrons. Yes. 6 lone pair electrons. Here is bonded electrons, 2, so half of them. So nitrogen came with 5 and now it has 7 electrons. 5 minus 7 is negative 2. Now, have a look. When we add up all these numbers, all the formal charges add up. Positive 1 plus 0 plus negative 2, it better add up to negative 1, the overall charge of the ion. Okay? So we have to do formal charge for all of the atoms and all of these structures to figure out which one is the best one. So let's do this again. Let's split up our bonded electrons. It makes it just easier quickly to do this. Okay, sulfur came with 5. Now it has 7, so negative 2 here. No, sulfur comes with 6. I'm so sorry. Sulfur came with 6. Now it has 7, so it's negative 1 here. Carbon comes with 4. Now it has 4. It has 0. Nitrogen came with 5, and now it also has 5 around it, so this is 0. And what's nice here is we're going to add up all of these numbers, and they do add up to negative 1. Okay, let's keep going. Sulfur, let's split up the bonded electrons really fast. All right. Sulfur comes with 6, and now it has 6. Here is 0. Carbon comes with 4. It has 4 around it, 0. Nitrogen comes with 5, and now it has 6 around it. 5 minus 6, -1. So far, so good. So here is the thing. Now I have formal charges on every atom, every structure. And remember, we want to be as close to formal charge to 0 as possible. Want to be as close to 0 as possible. Doesn't matter from what end on the number line. So that means right away that I can get rid of the structure because I have, why? Because I have -2 here. No other structure here has 2 spots away from 0. So this one, right away, the first choice, not good. Now I have a choice between second and third structure. Which one is the best? So here is the key. The more electronegative element will have a negative charge on it. So the more electronegative element, the one that pulls electrons more strongly to itself, will be the one with a negative charge. And if you look at your electronegativity values, you see that nitrogen is a little bit more electronegative than sulfur. So that means that this right here is my best choice. So there is no resonance here. It's just that the structure number 3, which is this structure right here, is the best choice right here. So we're going to use formal charge to explain the best choice. And on AP exam, they love to ask you about formal charge. So use formal charge to say why this structure is the best. Okay, so we went over a lot of material. We talked about expanded octets. We talked about ions to make sure you use brackets. We talked about elements, which are central atoms, which can have less than 8, less than an octet. We talked about resonance. We also talked about formal charge. That was a lot. You think you got it? I think you do. So practice a little bit. Thank you for watching and see you next time.